What does it mean when a comet seems to breathe? 3i Atlas, a traveller from another star system, is exhaling 40 kilograms of water every second in the freezing void, far too distant from the sun for such behaviour. Astronomers whisper, it's acting alive. But this comet's story doesn't end there. Strange nickel without iron, cyanide in its tail, and whispers of origins billions of years older than our own system. Meanwhile, away from this interstellar visitor, citizen scientists stumble upon the largest odd radio circles yet. Mercury and Ceres align with curious timing over the October skies, raising questions about a possible link with 3i Atlas, and Blue Origin's October flight raises more questions than answers. Did it even happen? Stay with me until the very end as we confront these unsettling questions in our first new multi-story format to keep our late-night listeners up to tabs with all cosmic news happening above our skies. If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The Impossible Signal. Picture this. You're floating in the cold silence of space, more than 3 times farther from the sun than Earth is. Out here, sunlight is a whisper. Ice stays frozen, comets go dormant, everything sleeps. And then you see it. A comet absolutely hemorrhaging water into the void, pouring 40 kilograms of the stuff into space every single second. Not a trickle, a flood. Water gushing off a frozen rock where water has no business flowing at all. This is 3i Atlas, an interstellar comet that arrived in our solar system from somewhere else, carrying rules from another star's backyard. And those rules? They don't match ours. The first clue came from SWIFT, a space telescope designed to hunt gamma-ray bursts. SWIFT turned its ultraviolet eyes toward 3i Atlas in early 2025 and spotted something impossible, a halo of hydroxyl molecules surrounding the comet. Hydroxyl, or OH, is what you get when sunlight rips water molecules apart. It's the echo of water screaming as it dies. When you see OH, you know water was just there, and SWIFT saw a lot of it. The numbers are staggering. At a distance of 3.51 astronomical units from the Sun, 3i Atlas was releasing 1.35 times 10 to the 27th water molecules every second. That's 40 kilograms per second. Every second. For context, that's like dumping a small car's worth of water into space every minute, at a distance where our comets barely whisper. Our solar system comets don't do this. Not out here. This far from the Sun, they're cold, dormant, practically dead. Water ice needs heat to sublimate, to turn directly from solid to gas without melting in between, and there's just not enough solar energy this far out to drive that kind of activity. Our comets wait until they're much closer to the Sun before they wake up and start streaming gas and dust into space. 3i Atlas didn't get that memo. You might remember Oumuamua, the first confirmed interstellar visitor. That thing was dry as a bone, no water, no outgassing, just a tumbling rock speeding through our neighbourhood. Silent. Then came 2I/Borisov, the second interstellar comet. Borisov was active, sure, but it behaved exactly like our comets do. It followed the script. It was predictable. It was boring, in the best possible way. 3i Atlas is neither of those things. It's alive in a way that shouldn't be possible. It's screaming water into space where silence should reign. And the question hanging over every astronomer who's pointed a telescope at this thing is simple. How? What mechanism could possibly drive this? Is there some exotic ice we don't know about? Something that sublimates at temperatures we thought were too cold? Is the comet's interior still warm from its birth billions of years ago? Is it rotating in some weird way that focuses sunlight onto hidden reservoirs of volatile materials? Or is there chemistry happening inside that rock that we've simply never encountered before? The water is just the beginning. 3i Atlas is also leaking other things: cyanide, nickel, carbon dioxide in concentrations that make no sense. Each new observation adds another layer to the mystery. Each spectral line that shows up in the data is another question mark. This isn't just a comet behaving oddly. This is a comet that seems to be operating under a completely different set of physical rules. Rules written in another star system, under different conditions, with different chemistry. And now it's here, in our solar system, giving us a front row seat to processes we've never seen before. The thing that keeps astronomers up at night is this. If 3i Atlas is doing things our comets can't do, what does that tell us about where it came from? What kind of star system builds comets like this? What were the conditions in that protoplanetary disk billions of years ago? And most provocatively, is this comet just weird? Or is it a messenger carrying news about how different the universe can be? Every telescope that can see this thing is now pointed at it. Spectroscopy, photometry, polarimetry, every tool we have. Because 3i Atlas isn't just a curiosity, it's a window, a crack in our understanding. And through that crack we might glimpse something extraordinary. Part 2. Nickel without iron. Comets are supposed to follow certain patterns. When they get hot enough, metals start to sublimate off their surfaces. Iron and nickel show up together, like old friends who always travel in pairs. You see one, you see the other. It's one of those cosmic constants we've come to rely on. Except 3i Atlas didn't read the textbook. The Very Large Telescope in Chile aimed its spectrograph at 3i Atlas and found something that made no sense. Nickel emission lines were blazing bright in the spectrum, strong, unmistakable, impossible to ignore. And iron, either absent or so weak it barely registered. Nickel without iron. It's like finding smoke without fire. It's like finding footprints without feet. In our solar system, this doesn't happen. When a comet heats up enough to release metals, iron and nickel appear in predictable ratios because they're locked together in the same mineral structures. They form together in similar processes. They sublimate at similar temperatures. They're chemically bonded in ways that keep them paired. But 3i Atlas apparently formed somewhere that plays by different rules. At around 2.8 astronomical units from the Sun, astronomers measured nickel pouring off the comet at about 5 grams per second. 5 grams doesn't sound like much until you realize it's happening continuously, second after second, with iron nowhere to be found. That's not a glitch. That's a pattern. That's the comet telling us something fundamental about its composition. Several explanations have been floated, and none of them are simple. The first possibility is chemical fractionation. Maybe in the environment where 3i Atlas formed, nickel got incorporated into volatile compounds that vaporize easily, while iron got locked into refractory minerals that need much higher temperatures to sublimate. Picture nickel hitching a ride with volatile ices, while iron stayed behind in rocky grains. That could create this decoupling we're seeing. Another idea involves organometallic compounds. On Earth, we have molecules like nickel carbonyl, where nickel atoms bind to carbon monoxide. These compounds are volatile, they evaporate at relatively low temperatures. If 3i Atlas formed in an environment rich in carbon monoxide and other organics, maybe nickel got trapped in these kinds of molecules. When sunlight hits them, they decompose, releasing atomic nickel into the coma while iron remains locked in solid grains. Then there's space weathering. Cosmic rays and ultraviolet radiation bombard interstellar objects for millions or billions of years. That kind of sustained assault can alter surface chemistry in weird ways. Maybe the radiation processing creates nickel-rich surface layers while iron gets buried or chemically altered. Maybe the nickel we're seeing is a skin, a radiation-damaged rind that doesn't reflect the comet's true bulk composition. Or maybe, and this is the most exciting possibility, 3i Atlas formed in a stellar system with genuinely different elemental abundances. Stars don't all have the same chemical makeup. Older stars, stars from different parts of the galaxy, stars that formed from gas clouds enriched by different types of supernovas, they all have slightly different recipes. Maybe 3i Atlas comes from a place where nickel was more abundant relative to iron than it is in our neighbourhood. Maybe its birth star was chemically odd, and that oddness is now written into every molecule of this comet. But we have to be careful here. Spectroscopy is hard. Detecting faint emission lines against a bright background is tricky. There are thresholds of detectability. It's possible that iron is there, just below the detection limit. Maybe the iron emission is blended with other spectral features. Maybe we're looking at the wrong wavelengths. As the comet gets closer to the Sun and heats up more, iron might start appearing. That would be reassuring in a way. It would mean the universe still makes sense. But what if it doesn't? What if 3i Atlas gets all the way to perihelion, the closest point to the Sun, and iron never shows up? What if the nickel-to-iron ratio stays completely inverted compared to everything we've ever seen? That would be revolutionary. That would tell us that planetary systems can produce comets with metal chemistry so different from ours that our models need complete overhauls. This is why astronomers are watching 3I Atlas so obsessively. Every observation is a test. Every spectrum is a chance to either confirm our understanding or shatter it. And right now, 3I Atlas is doing more shattering than confirming. Part 3. A comet that switches on. Comets are supposed to brighten gradually as they approach the sun. The physics is straightforward. More sunlight, more heating, more sublimation, more gas and dust. The relationship should be smooth, predictable, almost boring. 3I Atlas apparently never got that memo either. Observers watching 3I Atlas noticed something strange about its colour. Early on, the comet looked relatively neutral, maybe slightly reddish, typical of distant icy bodies. But as it moved closer to the sun, it started turning green. Not a subtle shift. A vivid, eerie green that became unmistakable in photographs. That green comes from two sources, cyanide molecules and atomic nickel. Both emit strongly in the green part of the spectrum, and both started ramping up dramatically as the comet warmed. The brightness increase wasn't linear, it wasn't smooth, it was superlinear, meaning the emission lines were intensifying faster than simple geometry would predict. When you halve the distance to the sun, you get 4 times the sunlight per square meter. That's inverse square law, basic physics. But 3I Atlas's emissions were climbing even faster than that. Something was being unlocked. Some new process was kicking in. Astronomers call this switch-on behaviour. Imagine a temperature threshold. Below that threshold, a particular ice stays solid, locked away, dormant. Then the comet crosses that threshold, and suddenly that ice starts sublimating. The gas production jumps. New emission lines appear in the spectrum. It's like flipping a switch. One moment the process is off, the next moment it's on. And once it's on, it can run away with itself if there's enough material to feed it. 3I Atlas seems to have multiple switches. The water turned on first, way out at 3.5 astronomical units, which is already anomalous. Then came the cyanide and nickel, blazing green as the comet warmed further. Each emission suggests a different volatile reservoir being tapped, a different chemical environment reaching its activation threshold. One model that might explain this involves extended icy grains in the coma. Instead of all the activity happening at the nucleus surface, imagine small ice grains being lifted off the nucleus by escaping gas. These grains float away from the comet, still cold, still frozen. But as they drift, they're exposed to more and more sunlight. Eventually, each grain reaches its own personal threshold and starts sublimating. This creates a distributed source of gas, not just from the nucleus, but from a cloud of icy grains surrounding it. That could explain the superlinear brightness increase and the sudden appearance of new emission lines. Another possibility is thermal fracturing. Comets are dirty snowballs, mixtures of ice and rock. When one part heats up and expands while another part stays cold and contracted, stresses build up. Eventually something cracks. When ice cracks, it can expose fresh material that was previously insulated. Suddenly you have new surface area sublimating, new volatiles escaping. The comet experiences an outburst. 3I Atlas might be cracking itself open as it heats, revealing layer after layer of frozen chemistry. Then there are the exotic ices. Water ice sublimates at one temperature. Carbon monoxide ice sublimates at a much lower temperature. Carbon dioxide is somewhere in between. If 3I Atlas is layered like an onion, with different ices at different depths or in different regions, then as it warms you'd see a sequence of activations. First the super volatiles, then the normal volatiles, then finally the really stubborn stuff. each layer peeling back like chapters in a book. This isn't entirely alien to us. We've seen comets in our solar system do weird things. Some comets have sudden outbursts, brightening by factors of 10 or more overnight. Some comets split apart as they approach the Sun, thermal stress overwhelming their structural integrity. Some comets stay dormant until very close to perihelion and then explode into activity. But 3i Atlas is doing this on a schedule that doesn't match our experience. It's alive at distances where it should be asleep. It's switching on in ways that feel almost deliberate. And the tension is building. As 3i Atlas continues its inward journey, will more switches flip? Will we see new emission lines appear, new molecules we didn't expect? Will the activity plateau, or will it keep accelerating? Every week brings new data, new surprises. This isn't a steady, predictable comet. This is a drama unfolding in real time. Part 4. Where did it come from? Every object in space carries a story written in its trajectory. Where it's going tells you where it's been, and 3i Atlas's trajectory is telling a story that spans billions of years and thousands of light years. The orbit is hyperbolic. That's the technical term for an open curve, a path that doesn't loop back. 3i Atlas came from interstellar space, swung around the Sun, and will leave again, never to return. The eccentricity is greater than 1, meaning this comet is unbound, a free agent, a wanderer. It's just passing through. Astronomers traced its path backward using precovery images. Precovery is when you search old survey data for images of an object before anyone knew it was interesting. Turns out 3i Atlas had been photographed multiple times by automated surveys, some images going back to when the comet was 6.4 astronomical units away, still inbound, still cold and distant. By stitching together these observations, astronomers reconstructed its trajectory with increasing precision. And that trajectory points outward, back into the galaxy. But not just anywhere. Orbital modelling combined with data from the Gaia Space Telescope, which has mapped the positions and motions of billions of stars, allows astronomers to make educated guesses about where 3i Atlas might have originated. The answer is surprising. The galaxy has structure. The stars aren't distributed randomly. Most stars, including our Sun, live in the thin disk, a relatively flat plane of younger metal-rich stars orbiting the galactic centre. But there's also a thick disk, a population of older stars that orbit in more tilted, more eccentric paths. These thick disk stars are vertically puffed up, spread farther above and below the galactic plane, and they're chemically different. They're older, formed earlier in the galaxy's history when there were fewer heavy elements around. They have lower metallicity. 3i Atlas's trajectory suggests it might have come from the thick disk. If that's true, if this comet formed in that ancient population, then it could be older than our solar system. Our solar system is 4.6 billion years old. Thick disk stars can be 7 billion years old or more. That means 3i Atlas could be carrying ice and rock from a time before the Sun even existed. Think about what that means chemically. The gas cloud that collapsed to form a thick disk star 7 billion years ago had fewer heavy elements than the cloud that formed our Sun. Supernova explosions enriched the galaxy over time, seeding it with elements heavier than helium. The earliest generations of stars had almost pure hydrogen and helium. Later generations, like our Sun, have a few % of heavy elements mixed in. Stars in the thick disk are intermediate. They have some heavy elements, but less than we do. If 3i Atlas formed in that environment, its composition would reflect that lower metallicity. There would be less iron, less magnesium, less silicon, all the rocky elements that build planets. But there would still be plenty of volatiles, carbon, nitrogen, oxygen locked into ices and molecules. Maybe that's why we're seeing such a high carbon dioxide to water ratio. Maybe that's why the metal ratios look weird. Maybe this comet is a chemical fossil from a time when the galaxy was younger and the periodic table was emptier. Of course, we can't be sure. Tracing an object back through billions of years of galactic motion is hard. Gravitational perturbations from passing stars, interactions with the galactic spiral arms, all of that muddles the trail. But the fact that it's even plausible that 3i Atlas is older than our solar system is extraordinary. We might be looking at a relic, a survivor, a time capsule from the ancient galaxy. And if we could pinpoint its birth cluster, the group of stars that form together from the same gas cloud, we might someday identify siblings. Other comets, maybe even planets, ejected from the same system, now scattered across the galaxy. 3i Atlas might be one letter, in a message written across thousands of light years, and we're just starting to learn how to read it. Part 5. What's riding along with it? Comets aren't just ice and rock, they're cargo ships carrying the molecular inventory of their birth environment. And 3I Atlas is carrying some very strange cargo. We've already talked about the water, 40 kilograms per second streaming off into space at distances where it shouldn't be flowing at all. That water, or rather the hydroxyl fragments left behind when sunlight rips it apart, was the first clue that this comet was unusual. But water is just the beginning of the story. Carbon dioxide is the real shock. Observations suggest that 3I Atlas has an extraordinarily high carbon dioxide to water ratio. In our solar system comets, water usually dominates. It's the main volatile, the primary driver of activity. Carbon dioxide is there, sure, but as a supporting player. 3I Atlas flips that script. Some measurements suggest that 95% of the volatile emissions are carbon dioxide, with water as the minority component. That's backward, that's inverted, that's nothing like what we see at home. Why would a comet be so carbon dioxide rich? One possibility is formation temperature. Carbon dioxide ice condenses at higher temperatures than water ice. If 3I Atlas formed in a warmer region of its protoplanetary disk, closer to its parent star, it might have preferentially incorporated carbon dioxide while losing some of its water. Or maybe the parent star's radiation field was different, processing ices in ways our sun doesn't. Or maybe the giant planets in that system, if there were any, migrated differently, stirring up the disk and mixing materials in unexpected ways. Then there's the cyanide. Cyanide, or CN, is common in comets. It's the molecule that gives many comets their green colour. But in 3I Atlas, the cyanide appeared after the water, later in the warming sequence. In our comets, cyanide and water tend to show up around the same time because they have similar sublimation temperatures. The delayed appearance of cyanide in 3I Atlas suggests it might be sequestered differently, maybe trapped in organic molecules that need extra energy to break down, maybe frozen in layers beneath the water ice. And of course, there's the nickel, atomic nickel glowing green, separated from its usual partner iron. We've already explored that mystery, but it's worth emphasizing again. Every element, every molecule we detect is a clue. Volatiles tell us about temperature and pressure during formation. Refractory materials tell us about condensation sequences and thermal processing. The ratio of gas to dust tells us about the comet's structure and how easily it breaks apart. Now, let's talk about the elephant in the room, the panspermia hypothesis. The idea that life, or at least the building blocks of life, can spread through space, on comets and asteroids. 3I Atlas has water, has organics, has cyanide, which is a key precursor in prebiotic chemistry. If you wanted to design a comet to seed a planet with interesting chemistry, you'd include exactly these ingredients. But let's be very clear, this is speculation. There's no evidence that 3I Atlas is carrying life. There's no evidence that any comet has ever carried life. The panspermia hypothesis is intriguing, plausible in principle, but unproven. And there are serious problems with it. Cosmic radiation is brutal. Over millions of years in interstellar space, high-energy particles tear apart complex molecules. Ultraviolet light from stars does the same. DNA, proteins, even simple amino acids can be destroyed. For life to survive an interstellar journey, it would need to be buried deep inside the comet, shielded by meters of ice and rock. But complex molecules might survive. Not living things, but chemical fossils. Molecules that were synthesized in the comet's parent system, perhaps in a planet's atmosphere or on its surface, and then got incorporated into the comet. Those molecules could survive the journey if they're stable enough and well protected. And if we could analyze them, they might tell us things we can't learn any other way. They might reveal atmospheric chemistry from an alien world. They might show us metabolic pathways from an extinct biosphere. They might be messages written in carbon and nitrogen and oxygen, waiting for someone to decode them. This is why some scientists dream of intercepting one of these interstellar visitors, not just observing it from Earth, but sending a spacecraft to match its velocity, to land on it, to drill into it, to scoop up samples and analyze them. The technological challenges are immense, Interstellar objects move fast, tens of kilometers per second. Catching one would require a spacecraft already in position, or capable of extraordinary acceleration. But the scientific payoff would be incalculable. A sample from another star system, chemistry from another corner of the galaxy, answers to questions we've barely learned to ask. 3i Atlas is already billions of kilometers away from the inner solar system. We didn't catch it this time, but it's showing us what's possible, it's showing us what's out there, and it's making us hungry for more. Part 6. Citizen Scientists Catching Ghosts. Sometimes the most important discoveries happen because someone was looking at the data in just the right way, not with algorithms, not with machine learning, but with human eyes and human intuition, and sometimes that someone isn't a professional astronomer at all. Let me tell you about odd radio circles, ORCs. If you haven't heard of them, you're not alone. They were only discovered in 2019, which in astronomy terms makes them practically brand new. ORCs are vast circular structures visible only in radio wavelengths. You can't see them in optical light. You can't see them in infrared. Point a radio telescope at the right patch of sky, and there they are. Perfect rings of radio emission, sometimes hundreds of thousands of light years across, floating in space like cosmic smoke rings. Nobody knows what they are. The leading theory involves galactic winds or shock waves from supermassive black holes, but honestly, we're still figuring it out. They're genuinely mysterious. And finding them is hard because they're faint and they blend into the radio background. Automated detection algorithms tend to miss them because they're trained to find point sources or compact objects, not large diffuse rings. Enter RAD at home. This is a citizen science project where volunteers visually inspect radio continuum maps, looking for things that don't fit. They're not looking for anything specific, they're looking for weird. And in March 2025, a volunteer flagged something extraordinary. The object is catalogued as RADJ 13134 6.9 plus 500320. Catchy name. But what it is far more interesting. A pair of intersecting radio rings, twin circles overlapping in the sky, creating a figure-8 pattern. It's the most distant and most powerful ORC discovered so far. And it was found not by an algorithm, not by a professional survey, but by someone volunteering their time to stare at data. The discovery was made using low-frequency continuum maps from LOFAR, the Low Frequency Array, a radio telescope network spread across Europe. LOFAR generates enormous amounts of data, too much for professional astronomers to examine by hand. Automated pipelines process most of it, flagging candidate objects based on brightness, shape, and other parameters. But those pipelines have filters. They have thresholds. They're designed to catch the expected, not the unexpected. This is where human pattern recognition becomes invaluable. Our brains are incredible at spotting things that don't belong, at seeing structure in noise, at flagging something as interesting even when we can't articulate why. The volunteer who found RADJ 13134 6.9 didn't need to know the physics of ORCs. They just needed to look at the image and think, that's weird. And they were right. But it's not just that one object. RAD at home has flagged multiple anomalies. Another volunteer found a giant radio galaxy with a peculiar ring structure around it. Another found a ring at the end of a jet, a feature that theoretical models didn't predict. These are objects that would have been lost in the data flood if humans hadn't been looking. There's a lesson here that extends beyond radio astronomy. We're entering an era of data deluge. The Vera Rubin Observatory, when it comes online, will generate 15 terabytes of data every night. 15 terabytes every night for 10 years. No human team can look at all of that. No set of algorithms can catch every anomaly. We need both. We need machines to handle the bulk processing and humans to catch the weird edge cases that don't fit any existing template. Now, let's connect this back to 3i Atlas. Could a citizen scientist have flagged its anomalies early? Could someone looking at spectral data have noticed the nickel without iron signature before professional astronomers did? Could someone monitoring comet activity have said, wait, why is this thing active so far from the sun? Maybe, maybe not. But the point is, anomalies like 3i Atlas benefit from having as many eyes as possible on the data. Professional astronomers have expertise, have training, have context, But they also have expectations, have models they're trying to confirm, have limited time. Amateurs and citizen scientists come with fresh eyes. They're not constrained by what's supposed to happen. They're free to see what actually is happening. There are stories of amateur astronomers discovering supernovae, finding asteroids, tracking variable stars. The Japanese amateur astronomer Kaoru Ikea discovered multiple comets and a supernova. The British amateur Andrew Gray co-discovered an unusual stellar outburst. These aren't flukes. They're examples of what happens when passionate people with telescopes or access to data decide to look carefully at the universe. In the future, as telescopes flood us with petabytes of data, citizen scientists might become the first responders to cosmic oddities. They might be the ones who flag the next interstellar comet, the next weird radio structure, the next thing that doesn't make sense. And when they do, professional astronomers will follow up, will investigate, will figure out the physics. It's a partnership. And like all good partnerships, it's stronger than either component alone. Part 7. Citizen science versus professional gatekeeping. But let's not pretend this is all sunshine and collaboration. There's tension here, real tension. Because opening the gates to citizen science means dealing with false positives, with well-meaning amateurs who flag things that turn out to be artifacts or noise, with conspiracy theorists who see alien signals in every data glitch. And professional astronomers, understandably, worry about this. The Royal Astronomical Society and other professional bodies have debated this extensively. On one hand, citizen science reduces the backlog. It allows projects to process more data than would otherwise be possible. It engages the public and creates enthusiasm for science. On the other hand, quality control is essential. A discovery isn't a discovery until it's been verified, cross-checked and peer-reviewed, and that takes time and expertise. False positives are a real problem. Someone flags an object as unusual. Astronomers spend days or weeks following up, only to determine it's instrumental noise, or a satellite trail, or a cosmic ray hit. That's time that could have been spent on genuine discoveries, and when false positives pile up, astronomers become skeptical of citizen reports. The signal-to-noise ratio drops, fatigue sets in, then there's confirmation bias. When people are looking for something specific, they tend to find it, even when it's not there. This happens to professionals too, but training and peer review provide checks. Amateurs might not have those checks. They might see a pattern in random data and convince themselves it's real. This is how you get claims of alien megastructures around Tabby's star or messages in pulsar timing residuals. Calibration and error margins are another issue. Professional astronomers know how to assess measurement uncertainty. They know when a signal is statistically significant and when it's noise. Amateurs might not. They might report a detection that's actually just a 1 sigma fluctuation, meaningless in the grand statistical scheme. And there's bandwidth. If a citizen science project becomes too popular, if too many people start flagging too many things, the professional astronomers tasked with follow-up can become overwhelmed. They can't investigate everything. They have to prioritize, and that means some genuine discoveries might get missed simply because they're buried in the pile. But here's the thing. These problems aren't insurmountable. They're challenges, not deal-breakers. Training protocols can help. If citizen scientists are taught how to assess data quality, how to recognize artifacts, how to estimate uncertainty, the false positive rate drops. Mentorship programs where experienced amateurs guide newcomers can maintain standards. Tiered validation, where multiple independent volunteers must flag the same object before it's elevated for professional follow-up, can filter out spurious detections, and the opportunities are enormous. Crowdsourcing anomaly hunts means you can search larger datasets more thoroughly. Cross-checking by many independent eyes reduces the chance that a real anomaly gets missed because one person was having an off day. Diverse perspectives mean people from different backgrounds might notice patterns that specialists overlook. Let's bring this back to 3i Atlas. Could a citizen astronomer have flagged its nickel anomaly early? The spectral data is public. Anyone with the right software can download it and look, but spectroscopy is hard. It requires understanding line identifications, wavelength calibrations, signal-to-noise assessments. It's not something you can do casually. But maybe, with training, with guidance, With a community of people working together, someone could have noticed the oddity before it made headlines. The same goes for the water production rate. Comet light curves, measurements of brightness over time, are often contributed by amateur astronomers. If those amateurs had been looking at ultraviolet data from Swift, and if they'd been trained to recognize unusual activity, patterns, they might have flagged 3i Atlas's superlinear brightening. They might have said, "This doesn't look like a normal comet," before professional surveys confirmed it. Past citizen-led discoveries prove this works. The exoplanet transit method, where you detect planets by watching for tiny dips in a star's brightness when the planet passes in front of it, has been advanced by citizen scientists analysing Kepler data. Projects like Planet Hunters have discovered multiple confirmed exoplanets. Amateur asteroid hunters have found near-Earth objects that professional surveys missed. Amateur nova hunters regularly beat professionals to the discovery of stellar outbursts because they're looking every night with small telescopes, while professional telescopes are scheduled months in advance. The conclusion isn't that we should replace professional astronomers with amateurs. That's absurd. The conclusion is that we need both. We need professionals for the deep expertise, the theoretical frameworks, the rigorous validation, and we need citizen scientists for the breadth of coverage, the fresh perspectives, the sheer number of eyes. It's not a competition, it's a partnership, and in the era of data deluge, it's a necessary partnership. Part 8. The Coincidence Effect. October 2025 brought something unusual. Excellent viewing conditions for both Mercury and Ceres. Mercury, the innermost planet, swung into a favourable evening apparition, bright and high above the horizon after sunset. Ceres, the largest object in the asteroid belt, reached opposition, meaning it was directly opposite the Sun in the sky, at its brightest and closest to Earth. On social media, people started connecting dots. Mercury visible, Ceres visible, and now this weird interstellar comet, 3i Atlas, acting alive. Were they related? Was there some cosmic alignment happening? Were the solar system's gravitational fields somehow triggering or amplifying the comet's activity? Let's be clear, no. There is no connection. Mercury's orbit has nothing to do with an interstellar comet's outgassing. Ceres's position relative to Earth has no influence on chemistry happening billions of kilometers away. These are independent events, coincidentally visible at the same time, nothing more. But people love patterns. We're wired to find them. It's a survival trait. Our ancestors who noticed that certain berries caused sickness and certain animal tracks led to prey were more likely to survive than those who didn't notice patterns. So our brains are hypersensitive to patterns, sometimes to the point of finding them where they don't exist. This is pareidolia on a cosmic scale. Pareidolia is seeing faces in clouds, hearing voices in static. It's pattern detection gone haywire, and it happens with celestial events all the time. Ancient cultures saw omens in planetary alignments. When a comet appeared during a battle, it meant the gods were angry. When planets gathered in one part of the sky, it signalled the birth or death of kings. 1910 provides a perfect historical analogy. That's the year Halley's Comet returned, swinging through the inner solar system on its 76-year orbit, and people were terrified. Astronomers had detected cyanogen, a toxic gas, in the comet's tail. Newspapers ran sensational headlines. Comet's poisonous tail will pass over Earth. People bought gas masks. Some sealed their windows. There were even reports of suicides by people convinced the comet would kill them. Of course, nothing happened. The comet's tail is incredibly diffuse, basically a hard vacuum by terrestrial standards. The amount of cyanogen that actually reached Earth was negligible, undetectable. The comet posed no threat. But the coincidence of the comet's appearance with other unrelated events, solar activity, political unrest, earthquakes, fueled the panic. People connected dots that didn't connect. We're seeing the same thing now with 3i Atlas. The comet is weird, genuinely anomalous. Mercury and Ceres happen to be visible at the same time, and suddenly people are constructing narratives. Maybe the comet is being awakened by some solar system resonance. Maybe its trajectory is being subtly altered by gravitational perturbations. Maybe this is all part of a larger pattern we don't yet understand. Astronomers have run the numbers. The gravitational influence of Mercury on an object in the outer solar system is essentially zero. Mercury is tiny, only slightly larger than our Moon, and it's far away. Ceres is even smaller and even less influential. The combined gravitational pull of every planet in the solar system couldn't significantly alter 3I Atlas's behavior at the distances we're observing it. The comet is doing what it's doing because of internal processes, solar radiation, and its own composition, not because of where Mercury happens to be in its orbit. But facts don't always matter when narratives are compelling. The human brain craves stories. We want events to be connected because disconnected events feel random, chaotic, meaningless. If the comet's activity is linked to planetary positions, then there's order, there's predictability, there's meaning. If they're unrelated, then we live in a universe where strange things just happen sometimes, and that's psychologically uncomfortable. Confirmation bias magnifies this effect. Once you start looking for connections, you find them everywhere. Mercury was also visible during a previous comet discovery. Ceres was near opposition when another unusual object was detected. Never mind that Mercury is visible several times a year, and Ceres reaches opposition annually. Never mind that unusual astronomical discoveries happen constantly. The brain filters out the non-coincidences and remembers only the ones that fit the narrative. Social media amplifies this exponentially. In the old days, if you had a theory about planetary alignments affecting comets, you might tell your friends, who would probably tell you it was nonsense, and that would be the end of it. Now you post your theory online and instantly find a community of people who think the same way. You share links, images, charts showing the alignments. Someone adds a new piece of evidence. Someone else shares it further. Before long, you have a full-blown alternative narrative competing with the scientific explanation. The lesson here isn't that people are stupid or gullible. The lesson is that coincidences are powerful, and our brains aren't well calibrated to dismiss them. Statistically, with thousands of astronomical events happening all the time, some will coincide purely by chance, and those coincidences will feel meaningful even when they're not. This matters because it affects how people interpret anomalies like 3I Atlas. If you're primed to see cosmic conspiracies, to believe that alignments matter, then the comet's weird behavior becomes evidence of something larger. Maybe it's not a natural comet at all. Maybe it's artificial. Maybe it's responding to signals from the planets. Maybe it's part of some grand cosmic mechanism we don't understand. And that brings us to an even stranger chapter in this story, the machinery of hoaxes, conspiracy theories, and how humans turn scientific mysteries into cultural myths. Part 9, October 2025. Update: Did it even happen? October 8th, 2025. Blue Origin mission NS-36. 6 passengers, 11 minutes. 1 mystery flyer whose name stayed secret until wheels down. The capsule launched, crossed the Kármán line, floated in microgravity, descended under parachutes, and touched down in the Texas desert. Success. Another flawless flight for the company's space tourism program, their 15th crewed mission. Routine, almost. That's the official story. ABC News covered it. Medium ran a piece. A handful of space journalists tweeted about it. The mystery passenger was revealed post-landing, a private individual who'd requested anonymity for the flight itself but was happy to be named afterward. Nothing unusual there. People pay for privacy all the time. But here's what's strange. Here's what keeps nagging at anyone who follows spaceflight closely. The silence. The eerie, almost suffocating lack of coverage. No viral videos, no trending hashtags, no celebrity reactions or memes or TikTok breakdowns. A spaceflight. A commercial crew crossing into the edge of space. Something that just a few years ago would have been headline news for days, barely registered a blip. Think about that for a moment. 6 human beings left the planet. They experienced weightlessness, saw the curve of Earth against the black of space, and returned safely. That's extraordinary. That should be extraordinary. But the internet shrugged. Social media moved on within hours. The story vanished like smoke. Why? Why so little documentation? Blue Origin usually releases cabin footage, beautiful shots of passengers floating, laughing, pressing their faces against windows. Where were those images? Why weren't they splashed across every news site? Why didn't the mystery passengers reveal generate curiosity? Who were they? Why did they want anonymity? These are natural questions, the kind that usually fuel days of speculation and interest. Instead, nothing. Radio silence. It's as if the flight happened in a vacuum, not just of space, but of public attention. And that vacuum, that absence, starts to feel like its own kind of presence. The silence becomes louder than any announcement could be. You start to wonder. You start asking uncomfortable questions. Did this flight really happen as described? Were there 6 passengers, or was the manifest different? Was the mystery passenger real, or a narrative device to explain the lack of pre-flight publicity? Did the capsule actually launch on October 8th, or was footage from a previous flight repackaged with a new date stamp? These are paranoid thoughts, conspiracy thinking. The kind of reasoning that sees shadows everywhere and trusts nothing. But sometimes, the absence of evidence feels significant. When something should make noise and doesn't, you have to ask why. Let's contrast this with April 2025, just 6 months earlier. Blue Origin launched another New Shepard mission, and that one exploded into public consciousness. Not because of a malfunction, because of who was on board. Katy Perry, Gayle King, the first all-female crew, high-profile passengers with millions of followers, the kind of flight that's designed to generate headlines. And it did. But not the headlines Blue Origin wanted. Within hours of the live stream ending, social media erupted with conspiracy theories. People claimed the flight was faked. They analysed every frame of footage looking for inconsistencies. Hair behaviour in zero gravity became a forensic battlefield. Does it float right? Does it move too stiffly? Is that real hair or a wig or computer generated? The capsule hatch became another focal point. Someone claimed it opened differently than in previous flights. They posted side-by-side comparisons, drew arrows, circled supposedly anomalous details. Wasn't the latch on the other side last time? Didn't the door swing outward before? Why does this look different? Then came the really wild stuff. Claims of green screens. Allegations that the passengers were filmed in a studio with fake windows showing pre-recorded Earth footage. Accusations that hands looked like mannequin hands, too smooth, too plastic. Complaints about the absence of visible scorch marks on the capsule after re-entry. Every tiny detail became evidence of deception. Journalists debunk the claims methodically. Hair behaves weirdly in microgravity because there's no gravity pulling it down, so it responds to air. Currents, static electricity, random motion. The hatch mechanism is identical across flights. Camera angles and lighting make it look different. Reflections in visors distort perspective. Scorch marks aren't always visible depending on landing site dust coverage and camera resolution. But debunking didn't stop the theories. If anything, it fueled them. People who wanted to believe the flight was fake interpreted the debunking as cover-up. They dug deeper, found more evidence, built elaborate models of how the hoax was perpetrated. The conspiracy became self-sustaining. Now we have 2 flights, 2 missions, same rocket, same basic profile, 6 months apart. One generated a firestorm of attention and doubt. The other barely made a sound. And you have to ask, which is more suspicious? Part 10. Space Mysteries as Mirrors. The universe keeps throwing us curveballs, objects that don't fit, signals that make no sense, phenomena that violate our carefully constructed models, and every single time, without fail, we do 2 things. First, we scramble to understand the science. Second, we project ourselves onto the mystery. Think about Oumuamua, 1917. First confirmed interstellar object passing through our solar system. Tumbling, reddish, elongated, and accelerating. Not much, but measurably, as it left the solar system. That acceleration didn't fit a purely gravitational trajectory. Something was pushing it. Scientists proposed outgassing. Even though no gas was detected, maybe Oumuamua was releasing small amounts of volatiles that created thrust, like a weak comet. Or maybe it was a hydrogen iceberg, frozen H2, which would sublimate invisibly. Or maybe it was a fragment of a shattered planet, its shape and spin creating radiation pressure effects. But a subset of people, including some scientists, proposed something else. What if Oumuamua was artificial? A light sail, a solar sail, a thin sheet of material being pushed by starlight. That would explain the acceleration. And if it was artificial, maybe it was a probe from another civilization. Maybe it was exploring, or maybe it was derelict. A piece of space junk from a long-dead alien society. The same thing happened with Tabby's star, KIC 8462852. A star in the Kepler field showing bizarre dimming patterns, deep irregular dips in brightness, sometimes dropping by 20% or more. No planet could do that. No planet is big enough to block that much light. And the dips didn't repeat regularly like a planet's transit would. Astronomers proposed dust clouds, swarms of comets, debris from a planetary collision. But one paper, half joking, suggested an alien megastructure, a Dyson swarm, millions of solar panels or habitats orbiting the star collecting its energy. That would block light irregularly as the structures moved. It fit the data, sort of. Odd radio circles, fast radio bursts, three-eye atlas. Every mystery becomes a screen onto which we project our hopes and fears. Are we alone? Is the universe indifferent or intentional? Are there others out there? And if so, are they like us or incomprehensibly alien? The psychology here is powerful. Pareidolia, seeing patterns in randomness, is part of it. We see faces in clouds, hear voices in white noise, and see intelligence in astronomical anomalies. It's not stupidity. It's the way our brains work. We're pattern recognition engines, and we're biased toward false positives. Better to mistake a shadow for a predator than to mistake a predator for a shadow. There's also existential longing. We want contact. We want to know we're not the only sparks of consciousness in a vast, cold universe. Every anomaly is a chance, a possibility, a door that might open onto something extraordinary. And so we push on those doors, and we do it hard. Three-eye atlas is a mirror. In its glowing green coma, we see reflected our own curiosity, our hunger for meaning, our hope that the universe is stranger and more wondrous than we imagine. And maybe it is. Maybe one day we'll find something genuinely inexplicable, something that forces us to rewrite physics or accept that we're not alone. But that day hasn't come yet. For now, we have a comet. A weird comet. A fascinating comet. But still, probably just a comet. And that's enough. Because even natural mysteries are extraordinary. Part 11. The Archive of Alien Systems. Imagine the galaxy as a library. Not a library of books, but of objects. Comets, asteroids, rogue planets, ejected during the chaotic formation of planetary systems and flung into interstellar space. Each object is a message in a bottle, carrying information about the star system where it formed. And occasionally, one of those bottles washes up on our shore. That's what interstellar objects are. Postcards from alien systems. Not alien in the sense of extraterrestrial intelligence, but alien in the sense of foreign, different, formed under conditions unlike those in our solar system. Every one we detect is a data point, a sample of one, and with enough samples we start to understand the diversity of planetary system chemistries. Our solar system comets are relatively uniform. They formed in the same protoplanetary disk, from the same well-mixed gas and dust, under the same stellar radiation field. They vary, sure. Some are more carbon monoxide rich, some more water rich, depending on where in the disk they formed and what temperatures they experienced. But they're family. They're siblings, cousins at most. Interstellar comets are strangers. They formed elsewhere, under different stars, in disks with different compositions, different temperatures, different dynamical environments. And so far, every one we've seen has been different. Oumuamua. Dry, non-outgassing, oddly shaped, accelerating mysteriously. It didn't look like our comets. It didn't act like our comets. If it was a comet at all, it was a type we'd never encountered. 2I Borisov, carbon monoxide rich. Fairly typical comet behaviour, but with a gas-to-dust ratio suggesting a colder formation environment than most of our comets. It looked familiar, but subtly off, like a dialect of a language you speak. 3I Atlas, water and carbon dioxide gushing at great distances, nickel without iron, cyanide appearing late. Nothing about its behaviour fits our experience. It's speaking a language we barely recognise. 3 objects, 3 wildly different chemistries. If we extrapolate, if we assume these 3 are representative of the broader population, then the diversity of cometary compositions in the galaxy is staggering. Not all planetary systems produce comets like ours. In fact, maybe most don't. Think about what that means. In some systems, comets might be dominated by nitrogen ice, like Pluto's surface. In others, methane might be the primary volatile. In systems with more massive stars, the snow line, the distance where water ice can condense, is farther out, so comets might form in colder regions and carry different volatile mixes. In systems with migrating giant planets, the disk gets stirred, mixing materials from different temperature zones, creating comets with weird, hybrid compositions. Could some comets carry molecules we've never seen? Molecules that are thermodynamically possible but require formation pathways that don't exist in our solar system? Exotic organics, strange ices, compounds that would make a chemist's eyes light up? Probably. The universe is big. The parameter space of stellar masses, disk compositions, radiation fields, and dynamical environments is enormous. Nature explores that parameter space thoroughly, and some of the results have to be strange. Now, let's take this a step further. If life requires certain chemical building blocks, water, organics, phosphorus, nitrogen, sulfur, then comets that lack those ingredients are sterile. They can't seed life. They can't deliver prebiotic chemistry to planets. Maybe many interstellar comets are sterile. Maybe Oumuamua was a lifeless rock tumbling through the void. But if even a fraction of comets carry the right chemistry, that fraction is important. Because comets are galactic wanderers. They travel between stars, they cross light years, and if they carry organic molecules, amino acids, maybe even dormant microbes shielded deep inside, then life's building blocks can spread across the galaxy. This is panspermia, the hypothesis that life can be transferred between worlds on comets or asteroids. It's controversial, it's unproven, but it's not impossible. And 3I Atlas, with its water, its organics, its cyanide, has the ingredients. Not life, probably, but the chemistry that could lead to life if delivered to a suitable planet. Every interstellar object we detect expands our sample. Right now we have 3. In 10 years, we might have dozens. In 50 years, hundreds. And with each one, we'll measure composition, trajectory, activity patterns. We'll build a statistical understanding of what's out there. Maybe we'll find that water-rich comets are common, that most planetary systems produce them. Or maybe we'll find that our solar system is the oddball, that water-rich comets are rare, and most systems produce dry, carbon-rich bodies. Either answer is fascinating, and maybe, just maybe, we'll find a comet with clear biomarkers, molecules that are hard to explain without biology, phospholipids, complex organics with chirality, isotope ratios that scream metabolism. That would be revolutionary. That would tell us life arose elsewhere, that biochemistry isn't unique to Earth. We haven't found that yet. 3I Atlas isn't carrying life, as far as we can tell, but it's carrying information, and information is the currency of science. Every interstellar visitor is a gift, a free sample delivered to our doorstep. All we have to do is look closely enough. Part 12. Nickel as a messenger. Let's return to that nickel anomaly, because it's not just a curiosity, it's a clue, a chemical fingerprint, and fingerprints tell you where someone's been. Stars are factories. Nuclear fusion in their cores takes hydrogen and helium and builds heavier elements, carbon, nitrogen, oxygen, silicon, sulfur, iron. And when massive stars explode as supernovae, the blast creates even heavier elements, including nickel. These elements get scattered into space, mixed into gas clouds, and eventually incorporated into new stars and planets. But not all stars have the same recipe. The abundance of heavy elements, what astronomers call metallicity, varies. Young stars formed recently from gas enriched by generations of supernovae have high metallicity. Old stars formed when the galaxy was young and fewer supernovae had occurred have low metallicity. Nickel and iron are both produced in supernovae, but in slightly different amounts depending on the type of explosion. Type 1. Asupernovae, where a white dwarf accretes matter and explodes, produce different nickel to iron ratios than core collapse supernovae, where a massive star implodes. If 3I Atlas formed in a system whose birth gas cloud was enriched by an unusual mix of supernova types, its nickel to iron ratio might be skewed. Now, we think 3I Atlas might come from the thick disk, an older stellar population. Thick disk stars have lower overall metallicity, but the ratios of different heavy elements can vary. If the nickel decoupling we're seeing in 3I Atlas reflects its parent star's composition, then that comet is a tracer. It's telling us about galactic chemical evolution in ways we can't easily access otherwise. Because here's the thing, we can analyse the atmospheres of stars spectroscopically. We can measure their iron, their nickel, their everything. But stars are far away. We can only study a tiny fraction of them, in detail, and we can't study stars that no longer exist, stars that lived and died billions of years ago. But comets from those systems, They're time capsules. They preserve the chemical conditions of their birth. If we could sample 3I Atlas directly, analyze its isotopes, its trace elements, its mineral structures, we'd be holding a piece of a star system that might be billions of years old and thousands of light years away. We'd be reading history written in atoms. Now, let's entertain a speculative idea. A fringe idea, but one that gets discussed in certain circles. Could metal anomalies like high nickel be signatures of processed material? Not natural processed, like thermal metamorphism, but technological processed. If an advanced civilization were mining asteroids, refining metals, building structures in space, they'd generate waste. Slag, tailings, exhaust. That material would have unusual elemental ratios because industrial processes are selective. You extract iron for construction, maybe, and discard the nickel-rich residue. Or you use nickel for some specific application and dump everything else. If a comet formed in a debris disk that contained industrial waste, it might incorporate those anomalous metals. And then, millions or billions of years later, that comet gets ejected, wanders the galaxy, and arrives in our solar system. We detect the nickel anomaly and scratch our heads. To be absolutely clear, there's no evidence that 3I Atlas is artificial or contaminated by technosignatures. None. The idea is speculative to the point of science fiction. Most scientists dismiss it outright. But it's not physically impossible, and in the absence of a clear natural explanation for the nickel-iron decoupling, even wild ideas get a hearing. The more likely explanation is prosaic chemistry, nickel in organometallic compounds, fractionation during condensation. Some process we haven't thought of yet that operates under conditions common in other star systems, but rare or absent in ours. But here's what excites me. Every comet carries a chemical signature, a barcode written in elements and isotopes. If we build a library of those signatures, if we catalogue the compositions of dozens or hundreds of interstellar objects, we can start to map the galaxy. We could correlate chemical signatures with trajectory. A comet coming from the direction of the galactic centre might have different abundances than one coming from the outer halo. A comet from the thick disk might show age-related signatures. We could use comets as tracers of galactic structure and evolution. Imagine a future where interstellar objects are so common, where our detection technology is so good that we're cataloguing them by the dozens every year. Each one gets spectroscopic analysis. Each one's trajectory gets traced back as far as possible. Each one's composition gets added to the database. Eventually patterns emerge. We find that comets from one region of the galaxy are systematically carbon-rich. Comets from another region are water-rich, and we start to understand why. Maybe carbon-rich regions formed more low-mass stars, which have different planetary disk chemistries. Maybe water-rich regions had more supernova activity, enriching the gas with oxygen. 3I Atlas is the beginning of that library. One entry, one data point. But it's a start. And the nickel, the strange, decoupled nickel, is a reminder that every data point has a story. Every element ratio is a clue. And if we're patient, if we're careful, we can read those stories and piece together the history of the galaxy itself. Part 13, The Unseen Population. 3 objects. Oumuamua, 2I Borisov, 3I Atlas. 3 confirmed interstellar visitors in the span of 7 years. That's not many, but it's enough to do statistics, enough to estimate how many more are out there, passing through undetected. Astronomers have run the numbers. Based on detection rates, survey coverage, and the observed properties of these 3 objects, they estimate that at any given moment, there are probably several interstellar objects within Jupiter's orbit. Small, dark, moving fast, invisible to most telescopes. We've detected 3 because we got lucky, because they passed close to Earth, or bright enough, or in the right part of the sky when the right telescope was looking. How many do we miss? Hundreds? Thousands? For every interstellar comet we detect, dozens probably pass through unnoticed. Some are too faint, some move too fast to follow up, some appear in parts of the sky we're not monitoring. Detection is hard, but it's getting easier. New surveys are coming online with unprecedented sensitivity and sky coverage. The Vera Rubin Observatory, currently under construction in Chile, will scan the entire visible sky every few nights, imaging everything down to incredibly faint magnitudes. It will detect asteroids, comets, supernovae, anything that moves or changes, and it will find interstellar objects. Estimates suggest Rubin could detect 1 interstellar object per month, maybe more. That's 12 per year minimum. In a decade, we'd have over 100 confirmed interstellar visitors. That's a statistical sample. That's enough to start drawing real conclusions about compositions, origins, populations. The Square Kilometre Array, a radio telescope network being built in Australia and South Africa, will also contribute. Radio observations can detect molecular emissions from comets, even faint ones. SKA could spot interstellar comets that optical telescopes miss. Space-based ultraviolet and infrared telescopes will catch comets that are active but obscured at optical wavelengths. Every new instrument expands our detection capability, our ability to see these faint, fast wanderers. But detecting is one thing, studying is another. Interstellar objects move fast, tens of kilometers per second relative to the Sun. So the time we spot them, analyze their orbits, and plan follow-up observations, they're often already leaving. Oumuamua was on its way out when we discovered it. We got one good look, and then it faded into the distance, too faint to observe. 2 Ice/Borisov we caught inbound, which gave us months to study it. Telescopes around the world pointed at it. We got spectra, light curves, detailed observations. That's the ideal scenario. 3I Atlas we also caught relatively early. We're getting good data, but soon it will reach perihelion, swing around the Sun, and head back into the darkness. And then it's gone, forever, unless we intercept it. There are proposals for interstellar object intercept missions, spacecraft designed to launch quickly, accelerate hard, rendezvous with an interstellar visitor while it's still in the inner solar system. The technical challenges are enormous. You'd need a spacecraft on standby, ready to launch on short notice. You'd need powerful propulsion to match the object's velocity, and you'd need instruments capable of analyzing composition, structure, maybe even collecting samples. But the payoff would be extraordinary. Imagine landing on an interstellar comet, drilling into its surface, collecting ice and rock from another star system, bringing it back to Earth for analysis in laboratories. The science we could do with that material is almost unimaginable. We could determine precise isotopic ratios, which tell you about nuclear processes in the parent star. We could analyze complex organic molecules in ways you can't do remotely. We could search for amino acids, for prebiotic chemistry, maybe even for fossilized microbes if we're incredibly lucky. Even if we don't find life, we'd learn about the chemistry of alien planetary systems in exquisite detail. Every molecule, every mineral, every isotope would be a clue. Some scientists are already planning such missions. Concepts exist. Budgets are being proposed. It's not science fiction. It's engineering, hard engineering, but doable. In 50 years, maybe 100, we might have catalogued hundreds of interstellar objects. We might have intercepted a dozen. We might have returned samples from half a dozen. And with that data, we'd have a comprehensive understanding of galactic comet populations, planetary system diversity, maybe even the prevalence of life's building blocks in the galaxy. 3I Atlas is a preview, a glimpse of what's possible. It's showing us that interstellar comets aren't just rare curiosities. They're common, they're everywhere, and they're carrying information we desperately want. The unseen population is out there, tumbling through the dark, waiting for us to find them, and we will. One by one, we'll catalogue them, study them, and piece together the puzzle of how planetary systems form, how chemistry varies across the galaxy, and maybe, just maybe, how common life really is. Part 14. When anomalies stack. Time 00.5s. Let's zoom out. Let's look at the bigger picture. Because 3I Atlas isn't the only weird thing happening in astronomy right now. Not by a long shot. Odd radio circles. Mysterious rings of radio emission. Origin unknown. Fast radio bursts. Millisecond duration pulses of radio energy from distant galaxies. Mechanism debated. Tabby's star. Bizarre dimming patterns. Not fully explained. Oumuamua. Interstellar object with anomalous acceleration. 3I Atlas. Comet with impossible water production and metal anomalies. And those are just the high-profile cases. There are dozens, maybe hundreds, of lesser-known anomalies. Transient events that don't fit known categories. Spectral features that shouldn't exist. Objects moving in ways that defy easy explanation. Astronomy is awash in things that don't make sense, and that's new. For most of the 20th century, astronomy was data-starved. You pointed a telescope at something, took a photograph or a spectrum, and spent months analysing it. Discoveries were rare. Anomalies were even rarer. When something weird showed up, it got intense scrutiny because there wasn't much else competing for attention. Now we're drowning in data. Automated surveys generate terabytes every night. Sky surveys catalogue billions of objects. Gravitational wave detectors record mergers. Radio telescopes scan the sky continuously. We're detecting more stuff than we can possibly follow up on, and with high volume comes high anomaly rates. If you look at 1 billion objects, even if only 1 in 1,000,000 is weird, that's 1,000 anomalies. Most will turn out to be instrumental artifacts, data glitches, misclassifications, but some will be real, and sorting through them takes time. We're in an era where anomalies outpace theory. We're finding things faster than we can explain them, and that's both exciting and dangerous. Exciting because new phenomena drive new physics. The discovery of pulsars, of gamma-ray bursts, of gravitational waves, all started with unexplained observations. Anomalies are where breakthroughs happen, but dangerous because hype cycles can spin out of control. Every anomaly gets hyped as potentially revolutionary. Alien megastructure, warp drive signatures, wormholes, dark matter interactions. The media loves it, the public loves it, and then, 9 times out of 10, the anomaly gets explained by something prosaic. Dust clouds, instrumental noise, misidentified known objects. The danger is credibility erosion. People hear potentially alien a dozen times and actually just dust a dozen times, and they stop trusting scientists. They start to think science is just wild speculation. Or worse, they double down on the alien explanation, deciding scientists are covering something up. Tabby's star is the cautionary tale. When the alien megastructure hypothesis made headlines, the public latched onto it. Social media exploded, news articles ran with it, and when follow-up observations showed wavelength-dependent dimming indicating dust, not solid structures, there was backlash. Some people accepted the explanation, others insisted the scientists were wrong or lying. But here's the thing, Tabby's star is still interesting. The dust explanation doesn't fully account for all the observations. Long-term monitoring shows complex variability. It's a weird star, possibly surrounded by a debris disk from a planetary collision, possibly doing something we don't entirely understand yet. It's still science. Still valuable. Just not aliens. The lesson is that anomalies are opportunities. They push us to refine models, to consider new mechanisms, to challenge assumptions. Even when they don't revolutionize physics, they advance it. Oumuamua's acceleration, even if it's just outgassing, forced cometary scientists to think harder about sublimation at low temperatures, about exotic ices, about surface properties. That's progress. 3I Atlas is another opportunity. Its water production challenges our understanding of volatile activation distances. Its nickel anomaly forces us to think about metal chemistry in comets, something we've largely ignored because our comets don't show strong metal emissions. Its carbon dioxide dominance opens questions about protoplanetary disk conditions in other systems. When you stack enough anomalies, patterns can emerge. Maybe odd radio circles and fast radio bursts are related, both involving energetic outflows from galactic centers. Maybe interstellar objects like Oumuamua and 3I Atlas represent distinct populations with different formation mechanisms. Maybe the transient zoo of astronomical phenomena is telling us something fundamental about how energetic the universe really is. Or maybe not. Maybe they're all unrelated, individual quirks that happen to occur in the same few decades because we finally have the technology to detect them. Either answer is informative. The key is maintaining skepticism and wonder simultaneously. You can be excited about an anomaly without claiming it rewrites physics. You can investigate weird possibilities without becoming wedded to them. You can change your mind when new evidence arrives. This is where good science communication matters. When reporting on 3I Atlas, responsible journalists and scientists should say, "This comet is behaving unusually. We're investigating several possible explanations. Here's what we know so far." Not, "Alien comet violates laws of physics." Not scientists baffled by impossible object. But nuance doesn't generate clicks, careful language doesn't go viral. And so the hype machine grinds on, turning every anomaly into a potential revolution, setting up disappointment when the mundane explanation arrives. The solution isn't to stop reporting on anomalies. The solution is to be honest about uncertainty, to present multiple hypotheses, to update when evidence changes. Treat the public like adults who can handle ambiguity, because they can. Most people understand that science is a process, that answers evolve, that we don't know yet is a perfectly acceptable response. 3i Atlas is one anomaly in a stack. It's important, it's fascinating. But it's not proof of anything yet. It's a data point, a mystery, an opportunity to learn. And whether it ends up being a weird natural comet or something we've never seen before, the process of studying it, of testing hypotheses, of ruling out explanations, is valuable. That process is science, and science, when done honestly, is one of humanity's greatest achievements, even when, especially when, it's grappling with things it doesn't yet understand. Part 15. Final Reflections. Alive, but natural. So here we are, thousands of words into the mystery of 3i Atlas, an interstellar comet pouring water into space where water shouldn't flow, glowing green with nickel and cyanide, switching on and off like something deliberate, carrying chemistry from another star system, possibly another epoch of the galaxy's history. Is it alive? In the poetic sense, maybe. It's dynamic, changing, responding to its environment. It's active when it should be dormant. It behaves in ways that feel purposeful even though we know they're driven by physics and chemistry, not intention. But alive in the literal sense? Almost certainly not. There's no evidence of biology here. No metabolic processes, no reproduction, no information storage and transfer, none of the hallmarks of life as we understand it. 3i Atlas is a rock covered in ice, heated by sunlight, releasing gas and dust according to physical laws. Yet those physical laws are producing something we've never seen before. Water sublimation at unprecedented distances, nickel without iron, carbon dioxide dominance, switch-on behavior that suggests complex internal structure or exotic ice compositions. Every observation adds another layer to the puzzle. So what is it? The most likely explanation is that 3i Atlas is a natural comet, formed under conditions very different from those in our solar system. Maybe it formed farther from its star, in a colder region where carbon dioxide ice is more abundant than water ice. Maybe its parent star had an unusual composition, leading to weird metal ratios. Maybe space weathering during billions of years in interstellar space altered its surface chemistry. The organometallic hypothesis is intriguing. If nickel got incorporated into volatile compounds like nickel carbonyl, that could explain the decoupled emissions. It would require specific chemical conditions during formation, but nothing impossible, just unusual. The thick disk origin is compelling. If 3i Atlas is 7 billion years old, if it carries isotopic signatures from an earlier era of galactic chemistry, that would explain some of the oddities. Ancient ice, ancient chemistry, ancient minerals, all preserved in the deep freeze of interstellar space and now being revealed as the comet heats. Could it be artificial? Could it be a probe, a derelict spacecraft, some technological artifact? The evidence doesn't support that. Nothing about 3i Atlas requires a technological explanation. Everything we're seeing can be explained, or at least potentially explained, by natural processes. Invoking aliens is unnecessary. But let's entertain the thought for a moment. If you wanted to design something that would survive an interstellar journey and still be detectable billions of years later, how would you do it? You'd probably use a comet-like object as a shell, protecting your payload with ice and rock. You might include unusual chemical signatures, markers that would stand out to anyone analyzing the spectrum. You'd let natural sublimation reveal those markers as the object approached a star. This is pure speculation. There's no evidence for it. But it's worth noting that if we ever do encounter an artificial interstellar object, it might not look artificial at first glance. It might look like a comet. A weird comet, sure, but explicable as natural until you dig deeper. 3i Atlas isn't that. Probably, almost certainly. But the fact that we're even asking the question tells you something. It tells you that this comet is strange enough to stretch our imaginations, to make us wonder, to force us to consider possibilities we'd normally dismiss. And maybe that's the real value here. Not whether 3i Atlas is natural or artificial, not whether its chemistry is merely unusual or genuinely revolutionary, but that it makes us think. It makes us question our assumptions. It reminds us that the universe is bigger and stranger than our little corner of it, that nature has had billions of years and trillions of star systems to explore chemical space, and that we've barely begun to survey what's possible. Every interstellar visitor is a challenge. It challenges our models, our theories, our sense of what's normal, and challenges are how we grow. Oumuamua challenged our understanding of cometary activity. 2i/Borisov challenged our assumptions about carbon monoxide abundances. 3i Atlas is challenging everything: volatile budgets, metal chemistry, activity distances, compositional diversity. The next steps are clear. Watch 3i Atlas as it approaches perihelion. Measure everything: spectra, light curves, gas production rates, dust-to-gas ratios. Look for new emission lines. Watch to see if iron finally appears or if the nickel anomaly persists. Compare observations to models, refine those models, generate predictions, test them, and prepare for the next interstellar visitor. Because there will be another and another. The galaxy is full of these wanderers, and our detection technology is getting better every year. Each one will be a new puzzle, a new set of clues, a new window into how planetary systems form and evolve across the diversity of stellar environments. Maybe one day we'll intercept one. We'll land on it, drill into it, bring back samples. We'll analyze its isotopes in terrestrial laboratories, study its minerals under electron microscopes, search its organic inventory for prebiotic molecules, and we'll learn things we can't even imagine right now. Until then, we watch, we measure, we wonder. Because that's what humans do. We look at the universe and we ask questions. Why is that comet active so far from the sun? Where did it come from? What can it teach us? The questions themselves are valuable even before we have answers, because questions are how exploration begins. 3i Atlas came from somewhere out there, across light years and billions of years, carrying a message written in water and nickel and cyanide. We didn't ask for this message. We don't know what it says yet. But we're listening, we're watching, we're learning. And in that act of learning, in that stubborn insistence on understanding, we find something that might be the closest thing to alive in this whole story. Not the comet, us, curious, wondering, reaching out to touch something that came from impossibly far away, trying to read a letter from another world. The universe keeps sending these letters, cosmic postcards, messages in bottles, visitors from the dark, and every time one arrives, we're reminded that we live in a vast, ancient, incomprehensibly rich cosmos. A cosmos that will forever outpace our understanding, forever surprise us, forever offer new mysteries. 3i Atlas is one mystery, one comet in an infinite sky. But it's our mystery now, and whether it's just a chunk of ancient ice or something more, whether its secrets yield easily or resist for decades, we'll keep looking, we'll keep asking, we'll keep listening for what the universe is trying to tell us. Because that's what it means to be human. To see something strange in the night sky and to refuse to look away. To demand answers even when the universe stays silent. To find wonder in a spray of water molecules 40 kilograms per second at a time, in the green glow of nickel that shouldn't be there, in the trajectory that points back towards stars we'll never reach. We are small. The universe is vast. But between us and that vastness, between our telescopes and those distant comets, between our questions and whatever answers we might find, there's a conversation happening. A slow conversation spanning centuries and light years, written in photons and spectral lines and orbital mechanics. 3i Atlas spoke. We heard it, and we're still listening for what it might say next.